Hi, my name's Mike Wooldridge. I'm a professor of computer science and artificial intelligence at the University of Oxford in the UK, and it's a very great pleasure to be with you today. What I'm going to talk about is a topic which is extremely active at the moment. It's machine learning. You will all have heard in the press on a regular basis that artificial intelligence has made some dramatic breakthroughs over the last 15 years. But in truth, those dramatic breakthroughs have happened mainly in one area of artificial intelligence, and that is machine learning. And there is speculation that these advances are really going to take us quite rapidly to a new era of AI. So what I want to do in this talk is to explain to you how those advances work. What exactly are these techniques that have become so successful in the last decade? And then what I'm going to do is go through some of the limitations of those techniques. What I want to do by the end of this talk is to get you to understand what really is the reality of artificial intelligence today, and what really is the reality of where artificial intelligence is going to take us in the next decades. So in summary then, we've seen a lot of progress in artificial intelligence over the last decade. There's a huge amount of investment, a huge amount of expectation in the community. I'm going to tell you where this progress came from, why this progress worked, and what it will and will not do. So the first question I want to talk to is, how do we do things in artificial intelligence, right? So we want to build a computer that can, for example, translate from one language to another or recognize faces in a picture. These are classic tasks for artificial intelligence. So how do we do it? Well, there are two basic approaches which have been studied very, very widely over the last 70 years since artificial intelligence was first introduced. And we can characterize these as being either top-down or bottom-up. So I need to explain a little bit about how top-down and bottom-up approaches. Broadly, all of artificial intelligence falls into these two categories, either top-down or bottom-up. So let's talk about the top-down approach. So suppose you want to build a program which is going to translate from, say, Russian into English. The top-down approach, which was the dominant approach from around about the mid-1950s through to the 1980s, says that what you should do is you should try to look at how a human would do this problem. Gather together all the expertise that a human translator would have and give that expertise to the computer. Right? So we would actually have to extract all that knowledge, all that expertise about how you do a translation and somehow give that to a computer. So this begs the question of how exactly you do that. And the main approach for extracting knowledge from humans and giving it to computers is to use what are called rules. And rules are discrete chunks of human knowledge, usually expressed in the form of a statement that says, if this is true, then this must be true. So they capture little bits of human expertise. And in some areas, this worked well. Where this approach works well is when you have very narrowly defined problems where there is a lot of human expertise at work and where that expertise is readily accessible. And so a class of systems that was studied very much in the 1980s right through to the early 1990s were what are called expert systems. A famous example of an expert system is a program called MySyn. And what MySyn does is it diagnoses the causes of blood diseases in humans. And what the developers of MySyn did is they talked to experts on blood diseases in humans and found out how they made their diagnosis. They expressed that knowledge in the form of these rules. If the patient has red spots and a fever, then it's Lassa fever with probability 0.3 would be a classic kind of rule. They gave that to the program, and the program was then capable of diagnosing blood diseases in humans. But there were many areas in which this approach didn't work terribly well. And one of the things that it's very, very bad at, this top-down approach, is dealing with problems of perception. And problems of perception are just making sense of what's going around you in your environment, interpreting speech, interpreting an image, recognizing a face in a picture. A perception is absolutely central in many fundamental artificial intelligence problems. Because, for example, if you look at the problem of driverless cars, we've seen a lot of progress recently. The core problem in driverless cars is simply the problem of perception. We need to somehow enable a car so that it knows where it is and what's around it. If you've solved that problem, the problem of deciding whether to stop or to speed up or to turn left or to turn right, those are all relatively trivial. All the difficult problems in driverless cars are to do with knowing what's around you and where you are. The problem of perception. And the top-down approach in artificial intelligence, trying to extract human knowledge and giving it to a machine, proved very, very bad at those problems. So the alternative to top-down is what I've called bottom-up, and this is machine learning. So in machine learning, what we do is we are completely concerned with learning an association, a mapping from some inputs to some outputs. So here is a classic example on the right-hand side of the slide. What we've got are a number of pictures of Alan Turing, the very famous Alan Turing, the British scientist who did so much to found the field of computer science and artificial intelligence. And the goal here is that we give the program a number of examples. We give the AI system a number of examples of pictures, and each picture is labeled with the name of the person that appears in it. And this is called training data. The training data consists of a number of pictures of Turing together with his name. And there may be pictures of me along with my name and you along with your name. And the goal is, after we've trained the program with this data, then when we subsequently present the program with a picture of a person, it can tell us who's in that program. Yeah. So what this is illustrating is that one of the most important lessons of machine learning is machine learning, for it to work, it needs training data. Okay, and that's a point that we'll come back to later on. The simplest kinds, or most straightforward kinds of machine learning, are what are called supervised learning. And supervised learning is where we're doing exactly what we do here. We're giving lots of training data. Here is the input, a picture of Turing, and here is the desired output, the name Alan Turing. And we give the program lots and lots of those examples. And eventually the program can produce the right output when subsequently given an input. But there are other kinds of machine learning, in particular what's called unsupervised learning. So in unsupervised learning, what we do is we simply let the program experiment. We let the program try things out, and we simply tell it whether it's doing well or badly. Yeah? So the program tries to do something, either does well or badly, but we tell it whether it does well or badly, and over time it adjusts its behavior so that it tries to do better and better and better. And that's called reinforcement learning, another influential approach, and we'll see an example of reinforcement learning in a moment. Okay, so how does a program do machine learning? Well, the basic techniques, the techniques that have become very popular over the last few years, are what are called neural networks and deep learning. And so let's explain a little bit about neural networks and deep learning. So here is a picture of a neural network. So the idea is that we take inspiration from structures that appear in human and animal brains. We're not, I emphasize, trying to build brains. This is not the goal of what we do, but we know when we look under a microscope at the structure of human and animal brains, they are populated by huge numbers of very, very simple information processing units, which are called neurons. And so what we do, and these neurons are the basis of human intelligence and in particular human learning. So what we do is we try to build software which mimics those structures. Again, I emphasize, we're not trying to build brains. We're taking inspiration from structures that appear in the brain. So let's have a look at a picture of a very, very simple neural network. In this neural network, each of the ovals represents one simple neuron. And you will immediately see that these neurons are connected to each other. So each neuron is taking some inputs, it's looking at some inputs that it's receiving, and depending on the particular pattern of those inputs, it's producing an output. And in particular, that output can feed into other different neurons. So you'll notice that each of these neurons are arranged into layers, and we've got 3 different layers here. So each neuron, each of the neurons on the left here, each of the 3 neurons on the left is looking at 3 inputs, inputs 1 through to 3, and depending on the particular pattern that it sees, and in particular on what's called the weights associated with those different inputs, it may generate an output. And that output then activates the next layer down in this neural network. Each neuron in the next layer is looking at the inputs it's receiving and maybe generating an output which is activating neurons in the next layer, and so on. And depending on what goes on, we may get some outputs. So think of output 1 as being the name Alan Turing, and output 2 as being the name Michael Wooldridge, and so on. So the last thing to say is, what are those inputs? The way to think about those inputs are, think about them as like the pixels on a camera picture. Right? So when you take a picture with your smartphone, what happens is the picture that it's seeing is broken down into millions of what are called pixels, tiny colored dots, which make up the overall picture. So think of each of these inputs as being one of those pixels. And if this neural network does its job correctly, then it recognizes the people that are in the pictures that it's being fed. Okay, well, we're looking at a picture with just 3 layers and 9 neurons. In reality, of course, the human brain is vastly larger than that, many billions of neurons, and they are hugely interconnected with many, many, many different layers. So in reality, for them to be useful, neural networks have to be a lot bigger. They have to have a lot more layers. And here we're showing a neural network with 5 layers, with an input layer on the left. Think again, this is a picture, not coming out terribly well, but it's in fact a picture of a lion. Again, think of those colored dots as being each of the inputs, the colored dots that make up that picture as being each of the inputs. And then these layers are processing that image, each neuron either firing or not firing, depending on the inputs that it's receiving, feeding that into the next layer, and so on, until finally in the output layer on the right-hand side, we have lion or cat or dog and so on being recognized. Okay, so when we train a neural network, we have to arrange it so that it's able to do this recognition process. How do we train it so it can do that recognition process? Well, we give it lots and lots of examples of pictures, in this case of lions and cats and dogs. And what we have to do, the training process, is to do with adjusting the connections between these neurons so that they, when it receives an input corresponding to a picture of a lion, it produces the output lion. And that's the difficult process. Training a neural network is the difficult process in machine learning. And I'll come back and talk about how that works later on, or the main points of how that works. So that's an example of training a neural network and how neural networks actually do their work. Let's now talk about a system, a very famous system. And this was a system in 2014, which really opened my eyes to what was going on in this area of deep learning and made me realize that actually something really quite dramatic was going on, that we were really in quite new territory to do with machine learning. And this program was developed by DeepMind. DeepMind is a company, a UK AI company. They were acquired by Google for $600 million in 2014, at the end of, I think, beginning of 2014. And the program that I'm going to tell you about is a program that they developed to play video games. So the video games that it got to play were based around a 1980s video console, a very, very early video console, very crude by today's standards. It was an 8-bit console. Current consoles are 64 bits. The graphics on it were very crude, as you'll see in a moment when we see the video. But this console had, I think, 49 games that were developed for it. And what DeepMind did is they wrote one game that learned to play all of those different games. And in particular, it learned to play more than half of them better than any human could play. Okay, so superhuman level ability. But this is the interesting thing. If we'd approached this problem using the top-down approach, then the way we would have done it is we would have found somebody who was really good at playing Atari video games, and we would have asked them, how do you do it? How do you play your games? And we would have extracted that knowledge about how they played and given it to a computer program. That's not what DeepMind did at all. What they did is they wrote a single program which would go in with no knowledge of the games whatsoever, and it would just experiment. And you remember, this is reinforcement learning. It's just experimenting, trying things out, seeing what works, what doesn't work. And when it does something that works, when it does something that gets a good score, what it does is it immediately learns from that experience, and it makes it more likely to do the good thing again in future. So I emphasize, it doesn't know the rules of any of the games that it's playing. Okay, one program gets to see all of these different games. And the other things to take away are this: all that the program gets are the screen, the same screen that you or I see. In fact, just a list of numbers. It breaks it down into the pixels. This pixel is red, this pixel is blue, this pixel is red, and so on. That's all it sees. It sees the same screen that you or I see, and it gets the video feed. It gets the score of the game. It knows at any given point how well it's doing. And the controls are exactly the same controls that you or I use. So the controls on this console was a simple joystick with a one fire button. So let's look now at a video, and the video is of the DeepMind program playing the game of Breakout. And anybody under the age of 70, I think, will immediately recognize the game of Breakout. So if we could show the video now. So we see when the program starts, it's essentially making random moves. It doesn't know what it's doing, remember. Nobody's told it the rules of the game, and it's very bad. It's missing the ball an awful lot of the time. It doesn't do very well. And after a couple of hundred training episodes, essentially just playing the game again and again, it's now got better. You can see that it's hitting the ball a bit more reliably, but it's still missing. After a few more training episodes, it never misses. Right? It's reliably hitting the ball every time. It's never missing it. Remember, all it's doing is experimenting with its actions, essentially making random moves. When it gets a good score, that makes it more likely to do the same thing again. But then something really unexpected happens. The program discovered, after a bit more play, the best way to get a high score in the game of Breakout. And this is what it did. It discovered that the best way to get a high score was to get the ball above the wall, in which case those bricks would very, very, very quickly be knocked out. And it discovered that completely on its own. Nobody told it that. The programmers didn't know that that behavior was there in the game of Breakout. It just discovered that by playing and its neural networks being trained over time to make the best choice based on the experience that they had. Bricks in the wall at the top as quickly as possible, and really quite often it's useful. But after a few training episodes, it gets better. It's not perfect, but it gets better. It's much better now at bouncing the ball back and knocking out the bricks. After 400 training episodes, it never misses. It's reliably knocking out bricks. It's never, never, never missing. It's getting every single brick knocked out steadily. And all it's done, I emphasize, is it's just played, moving its joystick in random directions. And when it gets a score, it's discovered that that was a good thing to do, and it makes it more likely to do that again. But then something really remarkable happens. What it discovers is this: it can knock the ball above the wall, and suddenly it very, very quickly gets the score. And this is the most efficient way to get a high score in the game of Breakout. Now, this is a 40-year-old video game. The designers of the DeepMind program, they weren't brought up playing this game of Breakout. They had no idea that that was going to be the behavior of this program. DeepMind's program learned that behavior, that really quite remarkable behavior that we saw there. It learned that completely autonomously. Nobody told it that that was the quickest way to get a high score. It simply experimented until it found that that was the key to very quickly getting a high score. So what do we take away from this? Well, so the first thing we take away is that this was a huge achievement, right? This really was a breakthrough moment in artificial intelligence. And the really exciting thing about this is something which may not be obvious to you. What was exciting about this are two things. Firstly, the sensory input that the program got is just the picture of the screen, the same that you or I see. There were no tricks, right? There was nothing behind the scenes going on. It just saw the screen and it knew what the score was. And the second thing is nobody taught it how to play these games. It was just pure reinforcement learning, training a neural network, right, in exactly the same way. And what happened was when it made a good move in the game, the neural network would be trained to learn that good move. Okay? So these are remarkable things, but let's remind ourselves that this program has a number of advantages. Firstly, actually just knowing what the score is really quite a big advantage. Do you know what the score in life is for you? Would be my question for you to take home after this presentation. So knowing what the score is, and in particular, immediately being told whether you've done something good or bad is a huge advantage. Okay, that's a huge advantage for this program. But second, all that expertise boils down to is a huge long list of weights. And these weights are just numbers in the neural network, a huge neural network. In fact, there are multiple neural networks in that program, are just a big long list of numbers. And we don't know what those numbers mean. They don't mean anything to us. They only make any sense in the context of that neural network. So we can't look at that neural network and extract from it the same kind of knowledge that a human expert would have. So the program can't explain how it's learning. It can't tell us what its strategy is. It doesn't know it's playing a game at all. All it is a neural network which has been trained to produce the right output for the corresponding input. Okay, so there are limitations, and we'll come back and talk about what those limitations are. So neural networks are actually a very old idea. Originally, they go back to the 1940s. The reason that they have taken off over the last 15 years is, well, really three things. The first is some algorithmic breakthroughs, some scientific breakthroughs, and they're all to do with how to train big neural networks. The bigger the neural network, the more powerful it is in principle, but only if you can train it. And so we've got algorithmic breakthroughs that make it much easier to train neural networks now. But there are two other components to the machine learning revolution, which are just as important. The first is you need lots of training data, right? Remember, training data is essential. In the Atari game, it got its own training data just by playing itself endlessly, okay? By playing endlessly. But you need lots of training data. And finally, to train these neural networks, to use the algorithms to find the right weights so that it's making the best decisions, takes an awful lot of computer power. And it's really the last 15 years, computer power has become very, very, very cheap. So neural networks in particular are a breakthrough technique, particularly to deal with problems of perception, problems of interpreting our sensor data, our sensors, to understand what's going on around with us. The problems of understanding what's in a picture, who's there in that picture, and so on, all of that, understanding speech, all of those things are very well suited for neural networks. And of course they are, because that's how it works in human and animal brains. But they're not perfect, and there are some things that neural networks find it difficult to do. And we'll come back and deal with some of these a little bit later on. So the first is any problem which involves long-term reasoning. So in the breakout game, when you knocked the ball back up to the wall and knocked a brick out of the wall, you immediately get a reward for that. You see your score go up immediately. So you know knocking that brick out was a good thing to do. That's a huge advantage if you're trying to learn how to play the game of breakout. Okay? The problem is, what happens if the reward that you get comes a long time in the future? So, for example, I don't know if any listeners still smoke, right? Smoke cigarettes, regular cigarettes. I'm sorry if you do, because it's bad for you and you shouldn't do that, but you still do. Why? Well, you know that this is bad for you. It's a bad thing to do. It's a bad move to make in the game of life. But the negative rewards for that, the punishment that you get from that in terms of health conditions, is not going to arise until decades into the future. If you got that reward immediately, I think you would much more, in terms of poor health, you know, you suffered poor health the day that you smoked a cigarette. I think it's a safe bet that many of us would learn not to smoke much more quickly. So anything which involves long-term reasoning, by which I mean connecting the actions that we do now with the consequences of those actions are long-term in the future. And we're not great at that, right? Which is why many of us still smoke. In the same way, that's difficult for machine learning. Anything to do with poorly defined problems. So it's very difficult for programs to learn when you don't know what the rules of the game are, when you don't know what the task is. It's much easier if you know exactly what the challenge is that the program is supposed to be doing. These problems involving perception, as we've already heard, these were very, very difficult for these problems of perception were very, very difficult for artificial intelligence for many decades. Problems involving judgment as opposed to precise rules, right? Judgment is where there is no hard and fast answer to a problem. We don't know exactly what the answer is. It's a bit yes and a bit no, right? Somehow we deal with these cases in life. We deal with them reasonably successfully, but they're very difficult for computer programs to navigate. So dealing with conflicting information. And finally, it's worth pointing out that the Atari program is a computer game. It's not the real world. Now, it's fine to run an Atari video game for millions and millions of games, which is the kind of technique that machine learning uses now. Nobody gets hurt in that. It just soaks up an awful lot of computer time, but nobody gets hurt because it's not in the real world. But you can't use that technique, reinforcement learning, in the real world. You can't train a car to drive safely by putting it actually out on real roads and just letting it experiment. You know, the consequences would be terrible. So these reinforcement learning techniques are rather limited at the moment to their applicability. They work best in virtual environments. Okay, so that's one example. Let's have a look at another example. This is even simpler. So my challenge to you is we've got a dialogue between Bob and Anne. Bob says, "I'm leaving you," and Anne says, "Who is she?" Okay, so 6 words in that dialogue, but 6 poignant, rich words. And everybody listening to this immediately has a mental picture. Maybe this happened to you. Maybe this happened to you last night, in which case I apologize for bringing back bad memories, right? But all of us as humans in the human world can immediately relate to this dialogue. We can answer questions about it. So, for example, is Bob a nice man? Well, probably not very nice. Is Anne angry or is she sad? Well, probably both of those things. Fill in the details. What's going on in this story? Well, Bob and Anne are in a relationship. They may well be married. Bob has met somebody else. And fallen in love with somebody else and decided to leave Anne. So he's announcing that. And Anne is inferring just from his announcement, "I'm leaving you," that that Bob is leaving for another woman. We can fill in all of those details without being told anything more about it. Computer programs don't have all that background knowledge of the human world because they're not humans and they haven't lived in the human world. If you give those 6 words to Google Translate, you can translate them from English to French, from French to Russian, from Russian to Arabic, and then from Arabic back to English, and you'll get the same 6 words back. But nowhere at any point in that process is the same rich mental picture that you all immediately had to explain and understand that dialogue. Okay. Now, my point is simply that, you know, if you want to build computer programs that, for example, can understand when people are going to get angry, and you know, if your computer program is going to be telling somebody whether they're going to get a bank loan or not, you better be able to understand whether they're going to get angry. You would need those kinds of capabilities. So this is, and we don't understand how to give those to computer programs because we all got them from the human world. Computer programs aren't in the human world. Okay, here's another example. And my question is, here's a linguistic example. Who does they refer to in these 2 examples? The committee denied the group a parade permit because they advocated violence. The committee denied the group a parade permit because they feared violence. So my question is, who does the word they refer to in each of these 2 sentences? They, the people that are advocating violence in the first sentence, are clearly the the group, right? The ones that fear violence are clearly the committee. So changing the one word in both of those sentences, in each of those sentences, completely changes the meaning. But the approaches that we've seen, these kind of neural network techniques, are very bad at picking up those kinds of subtleties in sentences. They're called Winograd sentences, and computer programs are very, very bad at being able to handle them. So why? Because in order to interpret those sentences, you need some knowledge of, for example, parades, and what parades do, the fact that they often lead to violence, and what committees do. Committees tend to avoid violence, and so on. You have to have all of that knowledge in order to be able to interpret those two sentences, and we don't know how to give that to a computer program. Okay, so next example. What's going on in this picture? Well, probably for a non-English audience, a bit of explanation. The character on the right in this picture is a famous English actor called Matt Smith, and he's playing a character called Doctor Who, who appears in a science fiction TV series in the United Kingdom, a BBC science fiction series in the UK. You won't recognise the character on the left. He's my late grandfather-in-law. Okay, so I've told you that the chap on the right is an actor. So let me ask you some questions. What's in his pocket there? So down at the right, there's some rolled up bunch of papers. What is in his pocket? Well, if you know he's an actor, then it's a pretty safe bet that it's a script, right? What is he holding in his hand? He looks kind of relaxed. I would hazard a guess that he's on a tea break. So the United Kingdom shares with Russia a great love for tea. He's almost certainly drinking tea. So he's on a tea break. He's not. He's probably therefore not filming. If I asked you what was around them, well, you know, you can now guess they're on a film set. So there would be cameras, there would be lights, there would be a catering truck. All of that you can start to fill in just from me telling you that he's an actor. And therefore, this must be a script. This is probably a cup of tea. Around them are cameras and lights and so on. And you can start to fill that in without any more knowledge at all. I'm not giving you anything else. You're just using your knowledge and using that to fill in around this picture. So let's see what a machine learning program makes of this. So here we have the same picture. I've just fed it to a computer program which interprets pictures. And it says, I think it's Matt Smith posing for a picture and they seem to be smiling. Well, that's very good, right? It's recognized Matt Smith, but it hasn't got any further than that. It's recognized Matt Smith, but it hasn't got any further than that. So remember, all that neural network is doing is it was looking at that picture and producing the text Matt Smith. But that's a part of understanding, but it's not a very deep part of understanding. It's missing an awful lot of the kinds of understanding that we would have. Remember, it's just a neural network which has been trained to produce the text Matt Smith when it sees a picture of Matt Smith. It's not doing everything else that a person would do. Okay, let's have a look at another example. So here's a famous picture. This is Starry Night by Van Gogh, French painter, early 20th century French painter. It's a very, very famous picture. What does it mean? What did the artist intend in that picture? Now, I couldn't begin to answer that question. I simply don't know what the artist intended. So if we feed the same picture to CaptionBot and ask it to explain, it doesn't even know that it's looking at a painting. It says, I think it's a couple of animals that are in the water. Right? So again, all that neural network is doing is it's trying to find the best output for the input corresponding to this picture. And it's doing a very, very bad job of it. Okay, so it doesn't even know that it's not looking at a picture. Okay, so just to go back briefly to the Atari video game, the long-term reasoning, there's a game called Montezuma's Revenge where you have to do a long chain of reasoning in order to get to the best action to perform. And Atari's video game, DeepMind's video game playing program did very badly when it was presented with this game, Montezuma's Revenge, because the payoff, the reward that it got was a long chain of events into the future, and it could never learn an association between what it's doing now and that payoff that it's going to get at some point into the future. So that's just an illustration of that. That's the long-term reasoning problem. And finally, what else is missing? So let's go back to driverless cars. Waymo, the world's leading driverless car company, they're doing millions of hours of supervised learning. The program is the cars that they put on the road are not doing reinforcement learning. They're supervised learning, where somebody is driving, essentially driving with them and telling them what they are seeing. Well, what would a driverless car do when it sees something like this? This is a truck that's on fire. Now, for a driverless car, this is just an obstacle. And what a driverless car is trained to do is to go around obstacles. You would never do that, right? You would immediately see that this was a hazard in the road. You would stop and you would not drive past it. But if you've just trained your driverless car by looking at obstacles and driving around obstacles, then that's all your driverless car is going to do. It's going to simply drive around it, which is something very dangerous. So in other words, what computer programs that are trained in that way don't have is common sense reasoning. If we saw that, we have our human experience to call upon. All the years of experience in the human world that we have used to try to understand new situations. In particular, any out-of-the-box thinking, experiences that are beyond the realm of the training that you've done with the machine learning program is going to be very, very difficult for AI programs to cope with. So the challenges then, the two different approaches that we've talked about to AI, the top down, we give all the expertise that we have to the program, and that's how the program makes intelligent decisions. And the bottom up, the machine learning, the neural network approach, we train the program either by giving it lots of training data. Here's a picture, here's the person that appears in it, or through reinforcement learning, the program trains itself. They both have limitations, but at some point, if we're to build really useful AI, we must find a way to be able to give those programs all that knowledge that we have of the human world, the knowledge of humans and human relations and human values, to be able to understand that 6-word dialogue, I'm leaving you, who is she? To be able to interpret, to really interpret what's going on with a picture. We need the bottom-up approach to be able to explain what it's doing, neural networks that can explain how they made a decision, to rationalize their decisions, to justify it, to encompass knowledge, to be able to take in knowledge of our world. In order for successful translation programs to do their work, we have to be able to give them the knowledge of, the author and what the author's concerns were, all of those things which humans make use of. At the moment, AI doesn't have, and at the moment, we don't know how to give AI those things. So I'm about done. I'd like to thank you for your attention. In this talk, I hope to have illustrated for you the genuinely exciting breakthroughs that we've seen in machine learning, and they are genuine. I don't mean to diminish them. They are genuine. They are exciting, but they are limited. They are not a magic ingredient to take us to some incredible new world of AI. We are still, when we try to build AI that is capable of human-level comprehension, human-level intelligent decision-making, we are still at the beginning of the road, I believe, despite all the breakthroughs that we've made. Thank you.